we discussed three converters: push-pull converter, the half-bridge converter, and the full-bridge converter. How do we design the transformers for these converters? We go by the area product method. We have discussed the area product method, and then we used it to design the forward converter, and we had developed generic area product equation. Using the generic area product equation, we can find out the area product of the push-pull. I will give you the final derived formula for the push-pull converter. Area product is equal to root 2 P naught 1 plus 1 by efficiency. Here efficiency is taken to be 0.8, worst case, so efficiency will always be better than 0.8, and the denominator you have 4 kW window factor J current density, which is 3 into 10 to the power of 6 ampere meter square. Bm for farads, it's 0.2 for the transformer, 0.2 Tesla, and then F as the switching frequency. So this is the area product for the push-pull converter. If you use the same generic formula and then plug in the voltage and the power voltage and power into the generic equation, that is the half cycle average voltage, you will get this. Likewise, for the half-bridge converter, the half-bridge converter transformer, also the area product I will be providing you here, derived along same lines, P naught into root 2 plus 1 by efficiency 1 by 0.8 divided by 4 kW J Bm and Fs. The full bridge converter, half bridge converter, the transformers are very similar, and the voltage wave shapes across the primary and the currents through them are all similar, and therefore you will have a similar area product equation. The difference, of course, will come in the actual values, the currents and the amplitudes of the voltage. So this is the area product for the full bridge converter. So you can try to derive these and verify them by using the same generic method for deriving the area products that we discussed for the forward converter as an example, and also the low frequency AC 50 Hz transformers too. So use all these transformers have the same generic basis. Let us now look at some M files for designing the push-pull converter, the half-bridge converter, and the full-bridge converter. So I have in the resources section a folder called M files. Within that, like for the forward converter, we had some common M files, that is the cores, the ferrite cores, the melt glass core, powdered iron core, and there is another M file on wires and wire gauges. So these are common for all the converter design in the sense that they are databases of the cores and the wires. You have three design files. One is the push-pull design.m, half-bridge design.m, and the full-bridge design.m, and these are the design M files which you can run, and they will make use of these cores, farads, wires, and other core and wire details from these other M files. So let me open the push-pull. So you see that here you have the push-pull design.m file, and it has a specification section. I have specified some things. Observe here, V0 is a vector of two elements, which means it is a isolated multi-output. There are two ORed secondaries. You have the delta V ripple and 1 amp and 0.5 amps for the two different outputs. Then you have the set of designer variables. I'm switching at 40 kilohertz here. 0.2 Tesla for transformer flux density maximum, 0.25 Tesla for inductors, Dmax of 0.45, which I have taken, 3 amp per mm square, or 3 into 10 to the power of 6 amp per meter square for the current density, and window factors I have chosen like this. So there is the power calculation, And after you do the power calculation, the turns ratio calculation, and this is where it will be different from the forward transformer design, which is the push-pull transformer. The area product of the push-pull transformer, I have taken it according to the area product of the push-pull that I have just listed down. And the part of the design is similar to that in the forward converter, where we call the cores, and the cores selects the cores, and then the wires for selecting the wire gauges, and cross check the design. Then you have the inductors for every output, isolated output. We have two isolated outputs, so 2 times it has to be done. So inductor value calculation, followed by energy calculation, then the selection of the core from the cores function file, and then the wires from the wires function file. Then you have the design of the capacitors, the output diodes, power switch, and then finally to display the results. So this is the push-pull design. I have given the specification here. You can go into Octave or even MATLAB for that matter, go into the respective folder, resource folder. I already have, and I have here full bridge, half bridge, and push-pull. So you type in push-pull design, and it will ask for the type of the core material. I am going to choose 1, which is ferrite. And then it will ask for the shape of the core material. I'm going to choose EE, and I'm going to choose 2. And you see here the area product calculated, and then the window area cross check is not fitting. So again, you will have to choose the next bigger size core. You can change the material if you want, but I will stick to ferrite. Go ahead with ferrite and the EE core. Let it choose the next higher one. It has chosen. Then it has gone for inductor of winding 1. I will choose ferrite and EE core to keep the same inventory list. Then inductor for winding 2. Again, you choose ferrite, and I am choosing EE core. And then that's it. The calculations are done and the results are displayed. You have the push-pull converter specifications, then the designer variables, then followed by the power switch ratings, diode ratings, inductor design with its core, air gap, all those things, capacitor filter ratings, and everything that is needed for rigging up the converter. So the push-pull converter design is designed in this fashion. I will allow you to play around with the specification and look into the equations and try to get more insight into the multi-output push-pull converter M file. Likewise, I have the half-bridge design M file. You can look into that also. I have kept the same specifications, and so that you can compare. Slightly I have changed the output specs, but otherwise I have essentially kept the same specification. Here also everything is same except for the half-bridge transformer design, the area product, which this equation will change, just like as I have listed shortly a while back. So you can execute this design like I did for the push-pull and try to find out the design values. I will just run it through half-bridge converter design. It goes in the same fashion. I will choose ferrite, E core, again ferrite, E core, ferrite for the inductor, ferrite inductors. So you will get the design values. You can read through the values later on, and here in the case of the half bridge, I am also calculating the flux walking capacitor ratings so that if you want to use the flux walking prevention using capacitors, you can use it. For small powers, this is really fine. In a similar way, I have also with me here the full bridge design M file. So very very similar, except for the area product. The area product in the case of the half bridge and the full bridge are same, so even those equations remain the same. You just have to run full bridge and do the same process of selecting the core, selecting the shape, and go through the process of selecting the core for the inductor shape, inductor 2 shape, and then you get the results. So just walk through the design design values. You will probably get a hang of the numbers for the typical design of the specification. So I will allow you to play around with the specs and try to get more insight into the design of the converters using this M file as a template.